Hi science students, we're going to discuss terminal velocity in this video. I'm going to show you this animation to begin with. So I'm going to drop this bigger object here. I'll just grab onto him for the moment. I'm going to take him up here now. I'm holding him up in the sky with my mouse. Now the weight of this object is 200 newtons. So the weight is equivalent to, but it's just the force of gravity that's acting on the object. And so that's the mass of the object multiplied by 9.81. Now at this point in time, the object isn't moving, so it has no air resistance. Now, when the object begins to fall, it'll start with an initial velocity of 0, so the air drag or air resistance will be 0. But as the object accelerates towards the Earth, that the velocity of the object will increase, and hence the drag will increase in the opposite direction to the weight. Now, this is a phenomenon that's quite familiar to you. For instance, if you're holding your hand outside the window of a car, not that that's an advisable thing to do, but if you were to hold your hand outside the window of a car that was going along at, say, walking pace, just driving up into a driveway or something like that, then you'd feel very little air resistance on your hand. But if the car was driving along really fast on the highway, then you'd feel a lot of air resistance because the car's going a lot faster, so you'd feel the air with your hand much more. So I'm going to drop this object and we're going to watch that air drag increase, and I'll explain when we reach terminal velocity. What terminal velocity means is that the object is no longer accelerating towards Earth. So I'm going to drop the object, and we can see that air drag increasing as the object accelerates, speeds up. Now at a certain point in time, that air drag will reach its maximum possible value in this context, which is equal to the weight of the object. And now, oh, not quite, now we've reached terminal velocity. So the object has stopped accelerating. Once the air drag becomes equal to the weight, the object is now traveling at a constant velocity until it hits the ground. So once air drag had become the same as weight, the net force acting on the object was now 0, and so the object stopped accelerating towards Earth. Okay, and that's when terminal velocity occurs. I'll just close that window up. We'll go back to this. So let's say we have an object. The moment that we drop this object, it will have weight, Fg or Fw, but no air resistance because it has a velocity of 0. But of course, as it falls towards Earth, this object will speed up. Its weight force, due to gravity, remains the same, but this air resistance will increase, or that drag. Now, at some point in time, as we discussed, that drag becomes equal in magnitude but opposite in direction to the weight of the object. So the net force at that point in time becomes 0. And when we have a net force of 0, our acceleration is also 0. Now that doesn't mean the object stops, and it still has motion downwards, but it stops accelerating, so it's now going to travel at constant velocity downwards. I'll leave you to have a look at this, the answers in the notes to this example, so go ahead and try that one. This is a skydiver jumping out of a helicopter. Just want to briefly discuss this one, because it can be a little bit confusing what's going on here. Now, the idea here at this first point in time is that this skydiver is traveling at terminal velocity. So there's gravity acting downwards, and upwards in the opposite direction is air resistance. Those forces are balanced, so the net force acting on this skydiver is 0, and hence the skydiver is travelling at terminal velocity. So we have terminal velocity. Now, this would be advisable for this skydiver to deploy their parachute before they hit the ground. So once that parachute is deployed, we start to see an increase, not in the weight of the skydiver, but an increase in the air resistance. At first, just very slight. I'll just make it slightly longer. So that black arrow is meant to be a little bit bigger now than the force due to gravity. So the net force is now upwards. Don't know how much, not going to worry about any calculations. So this skydiver begins to accelerate upwards. Now that doesn't mean they're moving upwards, they're still falling downwards, but they're slowing down from that point once the parachute is opened. Now once the chute's opened a bit more, there's going to be more air resistance. So I'll draw a big black arrow, and still gravity acting downwards, but much more air resistance. So the net force, F net, is going to be upwards but even bigger. So at this point the parachute person is accelerating even more rapidly upwards. Like I said, that can be confusing. They're actually still falling downwards, but their velocity is decreasing in the downwards direction. So they're decelerating, they're slowing down, but that's equivalent to accelerating upwards. Now in this last one, the chute is fully deployed, so now we are back to terminal velocity. However, it's a much slower terminal velocity than over here. Okay, so this can be confusing because students would say, well, wouldn't the parachute, because it's so big, wouldn't it have way more air resistance than the person when they were falling before? Well, it's built to have a great deal of air resistance, that's right. But remember, this person, their velocity is now a lot less, a lot slower. So the air resistance is going to be reduced as a result of that, and so it ends up being the same as when they were falling at terminal velocity before. So now the F net is once again equal to 0, so we have a new terminal velocity. Terminal velocity. However, this terminal velocity at the beginning was really fast. This terminal velocity now that the chute is open is much slower. So by increasing the capability of the air resistance of the chute compared to the person's body, you have a much slower terminal velocity, but same magnitude of forces acting in opposite directions. Okay guys, thank you for watching.